Good morning, everyone. My name is Isehaq Al-Nafai. I'm a PhD student at the University of Manchester. Today, I'm going to share with you part of my PhD project, which is about electrochemical investigation of novel zinc-rich organic coatings. Throughout my presentation, I will give you first the background of zinc-rich organic coatings, then my research objectives, moving to the methods and experimental procedure, result discussion, and finally concluding remarks. So as we know that zinc-rich organic coatings are the most used type of organic coatings due to two main reasons. The first one is the galvanic action, which is offered by the zinc particles. And the second one is the barrier effect, which is offered by the binder itself at the first stage of service, and then by post-cathodic barrier protection by the corrosion products. Zinc-rich organic coatings offer some properties. For the galvanic action to work properly, the zinc loading must be very high, not less and not greater than 8 to 8% in the coatings. And this is to ensure the connection between each zinc particles and between zinc particles and the steel substrate. But spherical and lamellar zinc particles can be used. Actually, if you use different sizes of spherical particles, this may give you better galvanic action, better connection. It depends on the requirement of each coatings. But the most well-formulated zinc-rich organic coatings, making the BVC is greater than or equal the critical pigment volume concentration to allow the best contact between each zinc particles. There is many advantages of zinc-rich organic coatings over the other coatings like inorganic or head-dip coatings, such as easiness to apply and can be applied with different top coats, does not need any regular surface pre-treatment, offers more flexibility, and require less curing conditions. However, there is still some problems associated with the high amounts of zinc in zinc-rich organic coatings, such as poor mechanical properties like cohesion, poor adhesion of the film to the substrate, poor coating leveling and zinc sedimentation, cost and environmental concerns, and most importantly, high amounts of zinc are lost without any reaction because they are disconnected from each other by the corrosion product of zinc. So recent studies seek to replace a part of zinc by conductive pigments such as graphene, carbon black, metal alloys, or carbon nanotubes, but the exact mechanism, especially the barrier effect, are not well established. That's why our objectives in this research is to propose new zinc-rich organic coatings by adding aluminum pigments and electrochemically study what is the effect of adding these pigments and to investigate what is the mechanism of protection and the role of aluminum in these added in these new formulations. So AkzoNobel provided us with these 5 formulations: the 100 zinc, which is the control one, then 30 aluminum, 70 zinc, 30 aluminum, 85 zinc, 15 aluminum, and 10 zinc, 10 aluminum coatings. The BVC of all these coatings is 55, so 100 zinc means that out of 55 is all zinc. For 70 zinc, 30 aluminum means out of 55 volume percent is 70 zinc and 30 is aluminum. The mean dry film thickness of all these coatings are about 70 micrometer. The appearance and morphology of the intact coatings, as you can see for the physical appearance, the higher the zinc, the darker the appearance, and vice versa for the aluminum content. And the SCM morphology, you can see the 100 zinc is loaded fully with about 88% for this one. As you can see, it's fully loaded with the zinc particles. For 30 aluminum, you can see that the aluminum flakes stack over each other like sheets. And then for 85, for the rest of the coating, zinc and aluminum coatings, you can see that aluminum flakes dispersed evenly between the zinc particles. The smaller the aluminum flakes, the smaller the gaps that are filled. Especially in this one here, you can see that smaller zinc flakes just in the vacancies between the zinc particles. This work included electrochemical tests like OCB versus time with BHD monitoring, electrochemical impedance, spectroscopy, anodic potentiostatic polarization, and the standard test includes salt spray test and immersion test. The characterization and analysis part includes XRD with Reitveld refinement before and after electrochemical test, and SEM, EDS, and mapping also before and after electrochemical test. For OCB measurement, I used 1 centimeter of each coating with a standard 3-cell electrode in 3.5 NaCl at room temperature. The edges of the sample is covered by lacquer to ensure only connection between the 1 centimeter area of the coating. The result shows that in comparison with the control zinc, the zinc aluminum formulation with 10 to 15 volume percent performs much better than the control one, as you can see here, for about 1,300 hours in comparison with the control, which is offer about only 200 of galvanic action. So the OCB test or gives you the indication what is the time of galvanic action these coatings can offer. So the longer the time below the OCB of the steel, that means more galvanic action offered by these coatings. So for the coatings with 10 to 15 aluminum content offers the more galvanic action. But for the higher one, which is 70 zinc 30 aluminum, higher aluminum content, it shows some fluctuation, and this is maybe because of local activation of zinc or accumulation of zinc corrosion products. The pH monitoring here was done to see what is the pH trend. So it starts rising at the beginning, and this is because the zinc dissolution, which is the anodic reaction in the coating, is balanced with the cathodic reaction of the oxygen reduction, which is producing the OH minus. So the pH of the media is increasing. And as we know that aluminum in normal state is passive, but when the pH is increasing, it starts to dissolve and offer some galvanic action. And this is the pH of the media. So I think the local pH inside the coating is a bit higher than this pH here. For the EIS of intact zinc-rich zinc aluminum coatings, the same setup as OCB experiment used here, but the frequency range was 0.01 Hertz until to 10 kilohertz with 10 millivolt amplitude at the OCB of the system. So the measurement was started, the first one immediately after immersion, and then after 3 hours, then after 24 increment until the first sign of rust appear, which is considered the moment of the coating failure. So this is an example of EIS measurement for 100 zinc code, the control coating. You can see that most of the measurements is 2-time constant, which are fitted with this circuit, the part with the coating and the other part for the metal in the higher frequency. To summarize the EIS measurement, I did the log impedance at 0.01 Hertz versus time. And as you can see here, there is a relative higher values of impedance for 10 to 15 volume percent of aluminum, which offer more protection. And up to this point, which is 1,300 hours, there is no sign of rust for these coatings in comparison with the control zinc or 30 aluminum coating. I also did this electrochemical test, which is anodic potentiostatic polarization, and it was done also with the 3 electrode cell setup in 3.5 NaCl at the OCB of the steel. And this is done to see for 2 things. The first one is to calculate the amount of metal dissolved or consumed in this time, and also to see how the current is passing and what is the period of current passing in these coatings. So you can see the broader or the higher the area under the curve, the more the zinc or the more the metals are dissolving in the coating. So the first one appears for the 100 zinc, and then for the 90 zinc 10 aluminum, and then for that one, which is 85 zinc 10 aluminum. Also, the highest value, the peak of the current, is happening at the same time of the lowest polarization resistance, which is indicates that the activation of zinc took place at that time when the peak is broad. That's mean longer zinc dissolution, and the broader peak here, I think it's for 90 zinc 10 aluminum. That's mean longer dissolution, or the galvanic action is prolonged by the addition of aluminum in this coating. The salt spray test was done in 5% NaCl for 1,000 hours. And you can see there is a relative better performance against corrosion for 85 zinc 15 aluminum and 10 zinc 90 zinc 10 aluminum in comparison with the control one and with the 70 zinc 30 aluminum. This is often no galvanic action at all, only a slight barrier action at the beginning of the service, and then it's failed. The XRD and Reitveld refinement done by bulk scanning of the coating from 10 to 90 degrees, and the Reitveld refinement was done by using GSAS software, GSAS2 software, and this software allows to calculate the relative amounts, usually in weight fraction, for each phase in any single XRD button. So for 100 zinc, after the electrochemical test, the only corrosion products zinc oxide and simonkalite, which is zinc chloride hydroxide. But for 30 aluminum, there is almost no reaction or no galvanic action for the aluminum, only some traces of aluminum hydroxide. In contrast, for zinc aluminum coatings, it shows that characteristic corrosion product, which is zakanite layer double hydroxide, which indicate that actually aluminum took place in galvanic action and dissolved some part of it to produce aluminum ions with zinc ions to form this crystalline corrosion products that help increasing the barrier effect or the barrier properties of these coatings. So there is no comparison between each coating because the software only calculate. You cannot compare this with that one in the numbers. So it's just for a specific XRD button. But you can see there is a high amounts of these two corrosion products, simonkalite and zakanite, in these zinc aluminum coatings. If we can go back here, there is no appearance of zinc hydroxide in the XRD button, which is supposed to be the first corrosion product in zinc dissolution. And this is because the presence of high amounts of chloride in NaCl solution with hydroxide ions from the cathodic reaction. So this is all produce the simonkalite, which is the main corrosion product, and also for over longer time, also zinc hydroxide that's formed at the beginning, also converted to simonkalite in the presence of high amount of chloride in the solution. The SEM analysis for each coating before and after the test allow us to see the morphology inside the coatings after the test. So this 100 zinc, it's full loaded of zinc particles with different size. After OCP test, you can see this is like sheets here, which is the simonkalite corrosion product. And you can see also much of the zinc particles are not reacted with, which is one of the problems that associated with zinc corrosion, zinc-rich coatings, that much of the zinc particles remain without any reaction because of the disconnection of the by zinc corrosion products. For 30 aluminum, you can see the sheets or the flakes of aluminum stack over each other, but after the water ingress and reach the steel substrate, it's completely failed with the steel substrate corroded heavily there, and without any changing in on the aluminum flakes in the coating. For 85 zinc 15 aluminum, you can see the steel substrate is almost intact with full corrosion products in the coating, and there is some like continuous bath of zinc dissolutions that indicate that actually much of the zinc also, although there is a high, still high amount of zinc unreacted, but most of them in some specific path are reacted and offer some galvanic action, with also accumulation of zinc corrosion product that's help increase the post-cathodic protection. The same situation with the 90 zinc 10 aluminum. Exactly, there is no apparent destruction for the steel substrate over this longer time of immersion. The same one here, but as you can see, for high amount of zinc, a high amount of aluminum, most of the zinc particles in contact with the steel substrate are not that consumed, and only the first part here. And I think this is before because the aluminum particle or aluminum flakes are passive and have no chance to activate and just disconnect between these zinc particles. After over more than 13, actually I think 1500 hours, you can see still the steel substrate are not affected, and the corrosion product are accumulated inside the coatings. What to note here is for 90 zinc 10 aluminum, there is some like baths inside the coating in some local areas, which may transfer the corrosion product in the surface and expose some of the fresh zinc particles to offer galvanic action. And that can be seen here in around each particles, there is a small amount of zinc oxide, which may offer the galvanic action for some time. So finally, the proposed protection mechanism of these zinc aluminum coatings, I can summarize it by two main properties: the cathodic protection and the galvanic and the barrier properties. So the addition of 10 to 15 volume% of aluminum seems to be very effective in zinc-rich organic coatings. So at the beginning of immersion, zinc particles were activated, offering galvanic action when the electrolyte wetting the coating. So a small amount of 10 to 15 volume of aluminum improve the structure by closing or by just filling the gaps between zinc particles, making the structure more compact and also enhance the electrical connection between zinc particles. Also, the current is passing for more time according to anodic potentiostatic polarization for 90 zinc 10 aluminum, indicating longer zinc aluminum dissolution, and the presence of aluminum prolong the galvanic action, and this can be seen by increased zinc corrosion products in these two coatings here. And this is also suggests that corrosion products are transferred, as can see in SEM image, transferred to the surface, which expose the rest of zinc particles to offer some more galvanic action. The barrier action, the flake-like itself of aluminum offers some barrier action at the beginning, but the corrosion products and amounts and structure are different, with high amounts of two main crystalline corrosion product of simonkalite and layered double hydroxide. So these corrosion products enhance the post-cathodic action protection. The problems with high amount of aluminum content is that it may increase the porosity of the coating and disconnect zinc particles, since most of the aluminum flakes are covered by passive oxide film and will not activate at the first moments of immersion. So the corrosion product tend to accumulate within the coating, preventing most of the zinc from galvanic action. So the concluding remarks, adding 10 to 15 aluminum% seems to be very beneficial in zinc-rich organic coatings, and the suggested mechanism that longer galvanic action due to compact structure and aluminum seems to enhance electrical connection and promote the production of crystalline corrosion products. And the high amounts of aluminum in 70 zinc 30 aluminum seems to decrease the performance due to porosity and due to the passivity and accumulation of zinc corrosion products at the very beginning of immersion, which prevent the zinc particles from sacrificial action. Finally, I just want to express my thanks to my supervisor, Professor Stuart Lyon, for his continuous guidance, support, advice, and encouragement through my PhD journey, and also appreciation extended to Chris Jones, Doug Beaumont, and Simon Gibbon from AkzoNobel for their guidance and assistance, and all AkzoNobel lab mates for their assistance during my PhD journey. And thank you so much for your listening.
Thanks very much, Isehaq. That's great. Any questions for the speaker? Here we go.
I'm old enough to remember Ken Ross, who was the head of the corrosion group at Manchester before the formation of the Corrosion and Protection Centre. And he studied zinc-rich paints, and he concluded at that time that the main role of zinc was to act as a cathodic inhibitor.
Yeah.
Because the zinc 2+ reacts with hydroxyl ions produced by the cathodic reaction and blocks the cathodic sites.
Yeah.
And looking at your pictures, it did look to me as though that was happening in your case, but you don't seem to have considered it.
I didn't get that one. So.
But there are two mechanisms of potentially protection. One is the galvanic protection, where the is polarized into the immunity region.
Yeah.
The other one is a conventional inhibition, where the zinc ions released by corrosion of the zinc cause inhibition of the steel. It's well known that zinc ions are very good inhibition. So the question is, did you consider the inhibition of the zinc ions as well as the galvanic protection?
I didn't consider it in the coatings, but I considered in separate experiment with only zinc ions and what's their effect in the inhibition of the steel substrate. So it seems that the zinc ions inhibit the steel substrate. So this may
sorry, I've got a follow-up question, if I may, if other people are desperate.
Yeah.
You talk about the aluminium improving the electrical connectivity. Have you measured the electrical resistance of the coating?
No.
It might be a good idea to do that if you're saying that it's changing.
Okay.
It's quite a simple measurement to do if you just coat the surface with this gold foil or something like that to get an electrical connection to it.
Yeah, but I think before the immersion, the aluminum is passive, maybe not does not connect the electricity that much.
Still do the experiment.
Okay.
Okay, though there's a connection. There's a question from the Odin audience. Have you tried different volume percentages, particle volume concentrations within the polymer?
No, just this one.
Okay, so a bit of context. These are marine coatings designed by AkzoNobel to an IMO specification, which is extremely tight and requires you to have particular components in it. The question I have actually, which is an inhibition question. Oops, I'm too close to the speaker here. I'll go over here. The question I have, which is worthy of consideration, is the zinc ions do inhibit, and you have checked. I know as supervisor you have checked that, but you are seeing this novel compound, this new aluminium zinc layered double hydroxide with carbonate in it. How does that influencing the material, the corrosion properties? Because you're seeing massive reduction in zinc release compared with 100% zinc. On your polarization, you're pulling out a lot of zinc, but with 10% aluminium, you're pulling out 10 times less zinc.
Exactly.
So why is that happening? What is the mechanism of the reduction of zinc pulling out?
You mean the formation of layered double hydroxide?
Yes. Do you think that is influencing the inhibition of the steel, but also the inhibition of the zinc corrosion inside the paint?
Yeah, because they will cover the zinc particles and then they inhibit them from any further reaction. Okay. So it's also inhibit the zinc particles and the steel substrate at the same time. Okay. Yeah.
Any other questions?
Yeah, mine is more like a comment or an idea rather than a question, because we saw a few talks about how pigments dissolve inside polymers. And while I was looking your talk, I thought that if you have conductive particles like zinc and you can measure the current, that's probably something that could be used to validate some of those models to get data on how things are connected inside the coating. So I wonder if some of your techniques could be potentially used for that.
You mean to measure the connection between?
Yeah, this sort of things.
I haven't done anything of that. Maybe I will consider it as the opposite.
So we've got two questions from the online audience again. Thanks for the nice talk. It says, what do you think the optimum shape of the aluminium pigment would be to aid with the optimum packing of the zinc particles?
The flake-like, I think so.
So do you think the flake is the optimum one, and you wouldn't go for any other shape?
I think the flakes, and also smaller flake, not the big flakes, because it will close the gap or filling the gap between zinc particles. So as you can see there, the zinc particle itself is with different sizes. So if we have some flakes-like, it just go between the zinc particles and just make the structure more compact and may enhance the electrical connection between them. Okay, so the last question from Douglas Mills. You mentioned the passive film in aluminium would interfere the galvanic action at 30%. And he's just wondering, surely that would also apply to the lower loadings of aluminium in the coatings. The aluminium is always passive. Yeah, but for the lower aluminum content, there is much. Yeah. So for lower content of aluminum, only small part of aluminum is found there. So even if it's passive at the beginning of the immersion, it does not, disconnect zinc particles. But you can see here that aluminum particles, aluminum flakes, make big, much of these areas here that disconnect between zinc particles. For example, here, between these and these particles are disconnected with high amount of aluminum there. But in this case, small amount of aluminum just in between the particles that help connect between zinc particles. Okay, thank you. Any final questions? Okay, one last question maybe before coffee, Yanwen.
Okay. I just wonder that the role of aluminium, if it is only filling of the volumes, can we change aluminium to talc or kaolin and to have the same action? Because if you put more aluminium, it looks like the conductivity is reduced. So I don't think the role of aluminium increase the conductivity. It might be only filling the volumes. Probably talc and kaolin is cheaper and can act as the same function.
Yeah, that's what I thought before. But as I said before, for longer immersion time, the pH of the medium is increasing. And I think the pH inside the coating is much higher than the medium. It reaches about 8. The pH is 8, which is the value that the passivity of aluminum is start to destroyed, and it may offer the galvanic action and connection at that time. So at the beginning, it's a barrier, right? But after longer immersion time, the pH is increasing and offers some dissolution of aluminum.